Okay, so this will be the last topic under chapter 2, electrostatic, and this is the most important application of electrostatic, the capacitance of a capacitor. So we all know that capacitance, this is the unit of capacitance is 1 farad, and 1 farad is this equivalent to the one charge, 1 coulomb for per volt that can be stored in a capacitor. So that's the capacitance. This is the capacity of the capacitor. So therefore, from this relationship, the definition of capacitance, we can say that C, which is the capacitance, is just equal to Q, which is the charge all over the voltage V. And the unit here will be in F, or farad. Now, the capacitance depends on the geometry of the physical geometry of the system, and also the property of the dielectric. That's the medium between the plates, because capacitors, these are just two plates. So let's just look at this one. So if we have two plates, this one and this one, let's make our upper plate to be the positively charged plate. Charges here, and let's make our here negatively charged plate. So there will be an electric field between these plates. Now let's neglect the fringing effect. When we say fringing effect, this is the electric field going through outside the area from where the plates are in parallel with each other. So that's fringing effect. If we neglect that, so the field will go into that direction. This will be our field. And if you remember, if we make this, before that, if we make the plates to be, the charge in the plates to be uniformly distributed, the charge density, so these are areas. So if the rho s is uniformly distributed, is equal to Q over the area. And from Gauss's law, D, if you remember our D, flux density, from Gauss's law, it says that this is just equal to the total charge all over the area. But in our case, the flux density is going to the same direction as our electric field, and it goes downward. So that, let's make it negative A Z. Then also, from our previous discussion, the relationship between the flux density and electric field intensity is just equal to D is just equal to epsilon times the electric field intensity. And you look at this one, I will not be using epsilon naught anymore. I will just put epsilon, because later on we will be having mediums that are not air. So in general, I'll make it epsilon. So this is true. Now this is also true. Then if I solve for E now, E, I know that D is equal to this one, negative AZ. So E will be equal to Q all over epsilon, which is epsilon naught times epsilon R, times the area here, E. That's the area of the sheet of charge, the plate. Next, so the direction will be also negative AZ. Negative AZ goes downward. So that is our E. Now, if I want to determine the potential, if the distance between these two plates, let's say the distance is D, if I want to solve for the potential between these 2 points, here and here. So if this is in the origin, 0, and this is in the distance D in the z-axis. So remember our formula for the potential. So this will be negative Q, or negative E dot dl. So if we integrate this, E dot dl, and our limit will be from this point to this point, so from 0 to D. And our DL, which is the vector, DL, we are only in the Z direction. This is just equal to DZ, AZ. And E is equal to this. So if we take the dot product between these two, we have the potential now will be equal to what? So we have negative and negative that will become positive. AZ, that AZ is 1. And the integral of, I don't have any DZ here in the equation, so all of them are constant. Integral of dz is just equal to z. And from 0 to d, so upper limit d minus lower limit 0. So I just need to multiply this with d. So this will be, voltage will be equal to q times d, which is the z. Upper limit, we don't have any lower limit, 0. The lower limit is 0. Q times d all over epsilon naught, epsilon r times the area A. And if we rearrange this in terms of, I'll divide both sides by V. So if I solve Q all over V, so I'll cross multiply. So this will become epsilon naught, epsilon R, A, and this will also go to the denominator. And what is Q over B? That is our capacitance. So we derive the formula of a capacitance, of a capacitor, epsilon naught, epsilon R times the area times D. So this is a vital formula for the capacitance. So remember, these are the three factors that affects the capacitance. We have the epsilon naught, epsilon R. This is dielectric constant. It depends on the dielectric, the medium. If it's air, epsilon R is just equal to 1. Your dielectric constant is just equal to epsilon naught. A is the area of the plate, and D is the thickness or the distance between the plates. And the unit here is farad. So now that we know this formula here, you can solve for the capacitance of every capacitor as long as you know the dielectric, you know the area of the plate, and the thickness of, or the distance between the capacitance. Okay, now what happens if we have, so in this case, this formula is only applicable if we have a, so for example, this is the capacitor. We have a plate here and another plate here. Then from here to here will be a voltage, plus or minus. Then this part here is the dielectric, and this is our thickness D. This will be our area. So this dielectric, most capacitors in electronic applications, they use mica, some ceramic capacitor also, and paper. And the dielectric constant for them is different for every medium. So here, this formula is applicable for a capacitor that has only one dielectric. What happens if we have multiple dielectric? What happens to the capacitance if we have multiple? So meaning, it's not just one dielectric. It's different dielectric in one capacitor. Multiple dielectric capacitors. So if I draw the cross-sectional, so this is the plates, and I have here the positive and negative. So we go to the voltage V plus minus. So we have, let's say, two dielectric. So this is the first dielectric. Can be paper or mica or simply air. And we have another dielectric here. So what will happen to the capacitance? To solve this, if this is the case, if you have this configuration, the equivalent of this is just like two capacitors connected in series. There are just two. You can solve the capacitance of this one and the capacitance of this one, C1 and C2. So the total equivalent here, the total C will be equal to C1 in series with C2. And remember our formula for series capacitors in circuits. How do you solve the equivalent of a series capacitor? It's the opposite of the way we solve for the resistors. So for resistors, the formula in parallel, we use that in the series in capacitor. So C is actually C1 times C2 all over C1 plus C. This is the parallel formula because they are in series. And if you solve for C1 here can be just equal to, using this formula here, we can name epsilon naught, epsilon r, we can name it 1 because this is C1. That's the relative permittivity of this dielectric here. Then next, we multiply that with the area. So the same area here. So just multiply it with A. They have the same area. All of them have the same area because they are in that configuration. All over the thickness. So let's call this one D1 and let's call this one D2. So all over D1, that's the C1. For C2, it's the same thing. We just change the subscript into 2, epsilon naught, epsilon R2, area all over D2. Okay, so epsilon R1, that's the relative permittivity for this dielectric. So epsilon R1, epsilon R2. So we can substitute that formulas here now. We multiply them first. So we have epsilon naught, epsilon R1, area over D1. You multiply it with epsilon naught, epsilon R1, area, or this will be 2, all over D2, all over, we add them, epsilon naught, epsilon R1, area, all over D1, plus epsilon naught, epsilon R2, all over D2, times A. And I simplify this to solve the formula. So the formula will be, so here we have epsilon naught squared, we have epsilon R1, we have epsilon R2 times area squared, all over D1 times D2. For the denominator, we can make D1 and D2 our least common denominator. So D1, D2 divided by D1 is D2. So this will be epsilon naught, epsilon R1 times A times D2, then plus epsilon naught, epsilon R2, A times D1. So we can cancel this and this. And we can also cancel that epsilon naught in the numerator and in the denominator. So that our formula, so this one, the epsilon naught and epsilon here. So the formula now for the capacitance, equivalent capacitance, will be epsilon naught, epsilon R1 times epsilon R2. We can also cancel the area here, area, common area, all over A, all over. Here, we only have epsilon R1 times D2. Then plus epsilon R2 times D1. This will be the general formula for 2. Dalawa to. This is 2 dielectric. So if you have more than 3, then you do it again. You can derive that thing using this formula. And what happens if the configuration, instead of just like that, the dielectric is cut here. So we have a dielectric here, and we have another dielectric somewhere here. So 2 dielectrics. So what happened to this type of configuration? So how do we deal with this one? So the equivalent of this will be, if this is in parallel, this one will be in series. So the two capacitance in series. If this is C1 and this is C2, they are connected, or they're connected in parallel. So the formula for C will be just C1 plus C2. They are in series. And the good thing here is they have the same distance, D here, D and D, but they have the different area. If they have an equal, this one and this one are equal, then they have different areas. So if you solve C1 will be equal to epsilon naught epsilon R1. So this is epsilon R1, this is epsilon R2. You multiply it with 81 all over D, the same D. For C2, epsilon naught epsilon R2, area 2 all over D. So if we add that, so our formula now, C will be equal to, so we have our common is D, LCD, and we just need to add, or actually we can factor out that common epsilon naught, and D. Epsilon naught all over D, and you need to multiply this with epsilon R1 times area 1 plus epsilon R2 times area 2. So this will be the formula for this type of configuration. So if the dielectric is in this configuration, and if the dielectric is in this configuration. So these are multiple dielectric. They can be more than 2. It can be more than 3. So if you more than 3 here, you just add them C1 plus C2 plus C3 and so on. You just need to add something here, plus epsilon R3 A3 plus epsilon R4 A4 and so on. So those are the capacitance in different dielectrics. Now let's look at the energy stored in a capacitor. We already know that the energy stored in a capacitor is simply equal to 1/2 C, the capacitance, times the voltage squared. This is a common formula that we are using since circuits 1. So I don't need to discuss that anymore. And you can now take examples. Or before we do that, some other formulas for this energy stored in a capacitor. We can also change this if we solve for the voltage or C, capacitance. We know C is equal to Q, C is equal to Q all over V. So if I substitute that here, another formula for the energy stored will be 1/2 Q. V will cancel out, Q times B. Another one is if I change V instead of Q. So if I solve for V here, V is equal to Q over C. So you square that, and the energy will be equal to 1/2 of Q squared all over C. The other C will cancel out, C squared in the numerator. So these are different formulas for different events. For the energy, these are energy stored in a capacitor, in a cap. And also, there's another parameter characteristic of, just like resistance, the opposite of resistance is conductance. For a capacitance, the reciprocal of capacitance, we call it elastance. Elastance. And usually we use letter S to denote this, and that's just equal to the reciprocal of the capacitance. And the unit for this, because the unit for capacitance is farad. So if you remember in resistance, conductance, the unit of resistance is ohms. Well, the unit of conductance before is the opposite of that, because they're opposite. This is mho, and this is ohm. For elastance also, they also make this one the opposite of this, which is the rough. So the unit of elastance is the rough or reciprocal of Farad or Farad inverse. It's the same thing. So we can have an example. First example. This one. Two metallic plates separated by 1 centimeter are connected across a 12-volt battery. A certain plastic material is inserted, completely filling the space between the plates and the charge of each plate observed to double. What is the dielectric constant of the plastic material? The plastic material that is inserted between the plates. So solution. So first, initially we have a free space, a capacitor that has a dielectric of a free space. So we can make our epsilon R1, make this one epsilon, our epsilon R1. And this is connected to a 12-volt battery. So 12 volts. And now, we insert a plastic between these plates. Insert. So we have a new dielectric here. So this is now the plastic. This is now epsilon R2. But still, this is connected to the same source, which is 12 volts. And we observe that the charge is doubled. So if we have Q1 here, we have another Q here, Q2. So the problem says the charge is doubled. So meaning Q2 is just equal to twice of Q1. And if you remember the formula of Q is just equal to C times B because C is equal to V over Q. So here, this is Q2, so this will be C2 times B. What's the voltage at 2? It's 12 volts. 12 for Q1. We have C2 times also the voltage is also 12 volts. So we can cancel that voltage, the same voltage. So therefore, it should be C1. So if the charge doubled with the constant voltage, then we can say that also the capacitance is doubled. So if the capacitance doubled, we can solve for C2 here from our formula epsilon naught times epsilon R. So the R here will be R2 times the area is the same. It's the same area and it's also the same thickness. They have the same area, the same thickness because the same plate are used. You only insert some dielectric between those plates. For C1, so 2 times epsilon naught. So this time this is epsilon R1, the area all over T. But remember, the first one is a free space. And what is the epsilon relative permittivity? When we are in free space, we just remove that one because that's just equal to 1. We just use epsilon naught. Remember that. So if this is epsilon R1, this is in free space or air, that's just equal to 1. We can also cancel out D and A and A. We can cancel out epsilon naught, and we can solve for the dielectric constant of the plastic material. So ER2 now will be just equal to 2. So this will be the dielectric constant or permittivity, relative permittivity of the plastic that is inserted in the capacitor. Okay, next example. Here, a capacitor has two parallel metal plates measuring 0.45 meter square each. The distance between the plates is 1 centimeter in free air. If a dielectric material whose permittivity is 4 and 5 millimeter thick is placed in the upper plate, leaving an air gap between the bottom plate and the dielectric. What is the capacitance of the capacitor? So solution. So in this case, first we have two parallel metal plates. So this one and this one. These are metal plates. So these are capacitors. They have the same cross-sectional area. Then between them is there is a 1 centimeter uh, free air, and a dielectric whose permittivity is 4 and 5 millimeter thick is placed in the upper plate. So we have an dielectric here and the upper plate, which is 5 millimeter thick. So this is 5 millimeter. We can call this one D, or simply D. And this is free air. This part is free air. So we have epsilon here, epsilon R, and that's just equal to 4. So this is 5 millimeter thick, and the area is 0.45 meters square, leaving an air gap between the plate and the capacitor. The distance between the plates is 1 centimeter. So the distance between the two is 1 centimeter, the plates. Then so we can just rename this. Instead of D, let's make this one T, and let's make the distance between the two plates be our D, and which is equal to 1 centimeter, that is 0.01 meters. 0.01 meter. This one is, let's make it all in terms of meters so that our unit are consistent. So we have 0. That's 5 millimeters, so 0.005 in terms of meters, because our area is 0.45 square meter. Then we have epsilon R here. Here, our epsilon R is equal to 0 or 1, so we have only epsilon naught. So this one, in this configuration, so if you remember our discussion, this is actually a parallel configuration. They are in parallel, these two capacitors here. There are two capacitors, the first one with the permittivity, the second one with the free space or air. So to solve for the equivalent capacitor, C, we can name the first one here C1 and this one C2. So this will be C1 times C2 all over C1 plus C2. And what is C1? C1 will be epsilon naught times epsilon R times the area. They have the same area, and the thickness is this one, T. And for C2, this one here, C2 will be epsilon naught times 1, because epsilon R is just 1, times the area, it's the same, and the thickness, that will be equal to D, the total distance from here to here, minus T. So this will be D minus T. You subtract this one here, and this will be D minus T. D minus T. Then we substitute that here in our formula, so we have C1 times that, so we have epsilon naught, epsilon R, epsilon naught squared, epsilon R times area squared, all over T times D minus T. Then all over, we add them. So we have T times D minus T, and this will be epsilon naught, epsilon R times A times D minus T. That's C1. Then plus this one, so T times epsilon naught A times T. Then we continue. We can cancel out this, and you can cancel out 1 epsilon naught here, and you can cancel out 1 area also. So what do we have? We have epsilon R times A all over, we have epsilon r also here, epsilon r times d minus t. Then we have plus, we only have t here, epsilon naught times A, cancelled out. And then we can have that formula already, or we can still try to simplify that formula. And we will have to simplify that. Actually, this is already okay. We can distribute epsilon r. Then we can factor out t if you want, but this is okay. Then to solve for d, you can memorize this as a formula. This is for with an air gap, with air gap, capacitors that has air gap, where t here is the air gap. Then given area, we already have area 0.45, given epsilon r, relative permittivity of the dielectric, which is 4, and we have area, we have d, and we have t. So the capacitance now will be equal to 4. Is that 4 epsilon r? 4, yes. Then you multiply it with the area. It's in meter, 0.45, so we don't need to convert that anymore. We are all in meters. All over epsilon r again, so that's 4. Our d is 0.01 meter. 0.01 minus our t is 1.005. 0.005. Then plus t again. 0.005. So our C now should be equal to, wait, I forgot the epsilon naught in the formula. I only cancelled out 1, so I have still 1 remaining, epsilon naught here. So I still need to multiply this with epsilon naught, and epsilon naught is just a constant. And I still don't get the answer, and I found out that this 0.45 here, it's a trick problem. This is a tricky problem. So if we try to observe the plate measuring 0.45 meters square each. So this is a tricky question because it's 0.45 meters square each. So this is not 0.45 square meter. So what's the difference between the two? 0.45 meters and square each. So it's a square with 0.45 measurement. So it means this 0.45 is just the side of the plate. So the area is not actually 0.45. The area should be 0.45 by 0.45. So I found out that this should be, the area should be 0.45 by 0.45 or 0.45. You need to square this so that your answer will be correct. And the answer will be 286.87 times 10 to the negative 12. 286.87 times 10 to the negative 12 farad. So this is the capacitance of this capacitor. Another problem, last problem. We have another one with multiple dielectric instead of air. Let's try that. So this will be our last example here. Okay, so example, a capacitor is composed of 2 plates that are separated by a 3 mm insulation. So that insulation is a dielectric. And whose dielectric constant is 4. So a dielectric constant, this is not the permittivity. This is not epsilon r1. This means that this is K. So K is just equal to, or simply epsilon, the electric constant, epsilon naught times epsilon r. So r here is, this is the relative permittivity, epsilon naught is the absolute permittivity. That's constant. And it says this is a dielectric constant of 4. So this is somewhat contradicting. Sometimes we call this one the dielectric constant, but actually this one is the permittivity. If you remember permittivity of the medium, of the medium. This is the permittivity of the medium with respect to the absolute permittivity epsilon naught. And epsilon r, this is the relative permittivity. Actually, this is synonymous with the dielectric constant. This is the dielectric constant instead of this k and this epsilon here. This is the permittivity of the medium. Epsilon r is actually the synonymous with the dielectric constant. So the 4 here is instead of epsilon naught times epsilon r. That's we can just make it our relative permittivity. So solution. So first, this is a capacitor that has the first one before we inserted the next insulation. So the first one, so we have the first dielectric epsilon naught. We can just call this one R1. And after that, we inserted some insulation again. And if this is, we retain this one, the original dielectric. So that's that. And we inserted another dielectric here. So this is another dielectric, another insulation. So this is the first one, epsilon R1, and this will be epsilon R2. So this is not the new capacitor. So before, this is D1. Let's call it D1. So this is still D1. And let's call this D2. And the condition says the capacitance of the capacitor decreases to half as much as its original value. So if this is C1 and this is C2, so what happens to the new value C2? This will be, it will decrease to half as much the original. So this will be 1/2 of C times 1. Or C1 is just twice of C2. And what is C1? What is C2? So we can solve that. C1 is epsilon naught, epsilon R1. The area is the same. We have the same area. All over the distance is D1. For C2, we have epsilon naught, epsilon R2, still the same area, and we have a distance D2. Then we can substitute these two equations here so that we have, or before that, the C2 that I'm talking here, this is wrong. This is not the C2. Because the new capacitance, we should include ER1 here, epsilon R1, not just epsilon R2. It's the both of them should be in the equation. So therefore, this is wrong. This is true if it's just the second, this one, this part here. But the new capacitance of this combination now, let's solve that. C2. Actually, we have the formula. We have already derived the formula here for parallel combination. That's a parallel combination somewhere here. This one, we can just use this. Just copy this one. This has two dielectrics, so we can use that to solve for the new capacitance, C2. So this will be C2. And epsilon R1 is this one, and so on, D1 and D2. Then we can substitute this in here. So we have C1 is epsilon naught, epsilon R1 area all over D1. And this is equal to epsilon naught, epsilon R1, epsilon R2 times the area all over epsilon R1 D2 plus epsilon R2 D times 1. Then we can cancel out. What can we cancel out here? These two, and even the area. Epsilon, epsilon. Then D1 and D2. So what's D1? D1 is the first one, 3 millimeter. Point D1 is 0.003. So D1 is 0.003 meters. D2 is 6 millimeter. So this D2 here is for ER2. So for here, that is also our D2 in our equation here. So D2 will be equal to 0.006. 0.006. Then epsilon R1 is equal to 4. The only unknown now in our equation will be epsilon R2. So we can now substitute that. So we have 1 over D1, which is 0.003, equals epsilon R2 all over epsilon R1, which is 4, multiplied by D2, 0.006, plus epsilon R2 times D1, which is 0.003. So we only have one unknown, and that is epsilon R2, or the dielectric constant of the second one. And this should be equal to 8. It should be equal to 8. If you solve that, that should be equal. You can check that. If there's something wrong with what I did here, the answer should be equal to 8. And that is our lecture on capacitor and capacitance.